I want to show you something here in web courses. Just before class, I learned that a few of you didn't know about it. There's a link to YouTube with my lectures recording straight from lecture. And the link to it is right here on the home page, right down here by the picture of Michael Faraday. And let me just click on it here. And it just opens up to the playlist. And it starts playing. That was my voice you could hear. And then just go over here and you can just choose which one you want to look at. Like here's yesterday's. And just go through the list and everything is in there. You know, remember the spreadsheet we did yesterday and we were talking about that and talking about this? It's all in there. And so, and every time you click something, it starts playing basically me with my big mouth. Anyway, so that's in web courses and you can do that. Get your clickers ready. We'll do some clicking here in just a second. Let me switch over to the laptop now. As you know, we have a midterm exam number 1 on Thursday. There's no class at UCF tomorrow. So this will be our last day to work on stuff. And we'll try to put, and if we don't get to everything in chapter 20 today, don't worry about what we don't get to. That'll be on, if we do anything more in chapter 20 after today, it'll be on exam 2. Okay? So the exam covers everything from the first day and on up until today, including today. So we're going to talk about electrical potential and electrical potential energy, and just to reinforce a few things. And then we're going to talk about circuits. But before we do that, I have a couple more things about our number 1 topic. I learned last night after class, I was hoping to learn about this earlier, but they didn't get through to me until later in the evening. Apparently there's a grades refresh method inside Wiley Plus that I can use. And here it is down here. And when you click it, it sends all of your guys' grades down into Canvas, our Canvas. So I used it this morning at 8:01 a.m. and actually I used it last night about 9 something. And it does seem to drop the grades down. So and it's pretty quick. So I you know, is there anybody that still, raise your hand if you still do not have a grade that you did in Wiley Plus and it's not showing up? Just a few of you. Oh, you know what else? It also tells me a list of people that did not synchronize. And so if you, let me think, what's the best way to do this? I'll tell you what I'll do. I'll put a discussion post up, and those of you that just raised your hands, you can post a reply, and that'll have your name on it, and just say, Dr. B, would you check my Wiley Plus, please? And I'll look on when I do the grade sync, it basically tells me all the successful synchronizations, all the submissions that go over to web courses. And there's about a dozen students just raised their hands, and there's about a dozen students that have had trouble. Everybody else, and they're marked in red, and everybody else has got green. So, a couple other things I want to mention to you, and that is sometimes in web courses, in messaging, and in discussions, I'll put a fairly short, brief message. It may appear terse or even brusque, And the reason for that is that usually I've posted something in discussions or announcements that will answer your question. So like this one, I got about 1,000 students yesterday. Dr. B, there's something wrong with my Wiley Plus grades. They're not showing up in the grade book, and different variations of that. So this message I sent out to about 1,000 students yesterday, and not meaning to be brusque or terse or anything, just because I had a whole lot of messages like that. So to write out a long letter and stuff is not practical. So when you get a message like this, check discussions, check YouTube. It means that the answer that you're looking for is on YouTube or is in discussions or maybe announcements. All right, so it's not that I'm trying to be a jerk ball. I mean, I do that easily enough, but I try not to do it in this. I don't use this to do that. All right, questions about that? Okay, another thing, the PDF from the DocCam yesterday is now available in, it's not a talking PDF, but I put it on the talking PDFs page. I think it's activated. I'll double check after a lecture. Anyways, if it's not there and activated, I'll make sure I activate it after lecture. We're going to do some DocCam today as well, and it won't be talking, so you'll just have to take notes, and I'll keep the podcast going so you'll at least hear the duration of my discussion. Office hours are going to be Wednesdays. We had a really nice office hour session today over in Java City, but breaking news, we are, due to popular demand, we are not going to use Java City, so that's... but we are going to use the sunroom at the Physical Sciences building. Here's the Physical Sciences building. And right by the main entrance there, if you turn left, the first room there is, and it's got a marker board and stuff. No coffee, but it does have and it's got comfy chairs and stuff. And it's a little more conducive than what we were doing over in Java City today, although we got a lot of work done over there, I think. So, and that'll be next, but same time, Wednesday, sometime after lunch, and then at some point we got to dip over here for a lecture. So 12:30-ish to 2:30-ish. Maya. It's Maya, right? Kiana, okay. Okay, sorry. Maya was in front of you. Yeah, okay. Yay. Yeah. She's that's good. That's good. Kiana, any idea of how many questions on the test? Well, let's see. It's a 50-point test. So if it were all basic multiple choice questions, it would be 50 questions and 50 dots. But it's not going to be that. Okay? So it's going to be, well, I'm trying to describe it, so it might be some number less than 50, and that's also, I'm not saying it to be facetious, I'm just trying to describe it. It's going to be something less than 50, maybe 25, maybe 40. It just depends on what I decide to do. Also, I'll probably give you a clicker question or two. And the benefit to the clicker question is the following. If I give you a clicker, like a calculation, calculate an electric field in magnitude, or calculate the tilt angle of an electric field vector, like the homework. And if you type in your answer and it's incorrect, but I can see what, like you forgot a factor of 2 or a factor of pi or something like that. I'll be able to see that in a clicker question and give you partial credit. And so I might make it a 5-point question, and if somebody, like forgets a decimal point, like if the answer is 40.7 and somebody types in 407, then I'll think, okay, they just -1, and they'll get 4 instead of 5. Okay, so I might do that, and that also decreases the number of scantron dots. So you'd have 45 scantron dots and 1 5-point clicker question. So we might do something like that. Okay, and the reason I can't tell you exactly is I don't have the test written. I always write it after the last lecture and before the exam. So I try to make it, as I always say, centered on lecture, and therefore I have to wait until after the last lecture, and sometimes until after the last office hours. But we're going to have office hours before lecture, so after the last lecture, I'll write. So tonight, tomorrow, I'll be writing it and then photocopying it and stuff. No, we had office hours today because campus is closed tomorrow. Remember, because it's 4th of July. So, but next week it's going to be Wednesday over here in the Physical Sciences building. If you haven't been to the Physical Sciences building yet, what you do is you go to the Student Health Center. You go out this building, you cut around to the left, and you go past the Student Health Center and then past the Counseling Center, and then at the shuttle bus stop, that's the Physical Sciences building. You can't really see the shuttle bus stop here, but. Another question. Okay, let's keep going. Last time we talked about electrical potential energy in general, and then we talked about parallel plates. And we also talked about voltage, the electrostatic potential. Here's the curve that corresponds to the electrical potential energy for a proton-proton system. All right, and so the electrical potential energy function graphed up here it's all positive. And notice that I've done the vertical axis here in units of electron volts. For atomic systems, molecules, electron volts is what you want to try to use if you can. And it's just a few single digits instead of whole bunch of scientific notation. But last time we did it in terms of volts and stuff, and it's pretty small. The other thing is that if you have an electron-proton system, so this is like the hydrogen atom, the potential energy can be negative, and that's a problem. Depending on what kind of a system you have, a proton doesn't have a defined potential energy. You have to know the charge of the other particle, whether it's a negative or a positive. So if it's a negative, you've got something like this. All right, now this one's and what this tells you basically is that the electron, this is the potential energy of the electron in an electron-proton system. The electron is going to dip inward. It's going to go naturally toward the proton. It's going to go to lower values of the potential energy. And the same thing here for the proton-proton system here. So this is like the makings of a molecule of hydrogen, basically two protons and a covalent electron, covalent bonding. Anyway, so this is a proton-proton system. This one's positive, and they like to move away from each other. So the region of lower potential energy is off towards larger r. Okay? It's smaller, and it stays positive the whole way. It's a 1 over r function. But because it's potential energy, it can be this, little bit of confusion if you're not careful between all positive or all negative. Now this one's all negative. It's basically the flip-flop of the one that we just looked at. And this is for the electron around a proton. And this one is also marked in electron volts. And notice that they're all negative. The ground state of the s orbital for the hydrogen is, for n equals 1, the ground state is negative 13.6 electron volts. So that's a little bit deeper than this chart, this graph. But you could graph it up if you wanted to. As I mentioned, it all depends on the other particle, whether it's a proton or an electron. Now, it's not something that I have in the slide, but it's something that we talked about in lecture in office hours in the library a few minutes ago. Compare this, and make a note, compare this to the gravitational potential energy. The gravitational potential energy is always, the gravitational interaction is always attractive. So it always looks like this. It's always going to a lower value and toward the central mass. So the potential energy of the sun for any planet is going to look like this, except that the units are not going to be electron volts. It's going to be many, many jillions of joules of potential energy. But it'll dip down, and so what that means is that every planet is going to want to go to towards the center. Now, the amendment to this is that once you get really close to the sun, other energy terms start to spring up. And so this is not the only energy curve in the gravitational system. And eventually, for an electron and for a gravitational system, this curve is going to dip back upwards. And that's kind of an advanced physics topic, but that basically is why things get stable orbits, stable gravitational orbits. But anyways, gravitational is always like this. There's no ambiguity about the gravitational potential energy. It's always, minus G times M times M1 times M2 over R. That's it. It's very simple, and you don't have to worry about, sometimes it's upside down of the other. It's not. It's always like this. But with the electromagnetic interaction, it's a little dubious, a little bit confusing. You just got to get used to thinking about it. That's all. Now, that problem does not hold with the electrostatic potential. And that's because the electrostatic potential is defined in terms of your source charge or your central charge. In this case, it's a proton. And this is the electrostatic potential, capital V of R, as a function of R, for a proton. The size of the charge is E, positive 1.602 times 10 to the minus 19 coulombs. K is good old 9 times 10 to the 9, Newton meter squared per coulomb squared. And then R is, whatever you want it in meters or nanometers or something like that. I've got it graphed up in nanometers here. Okay? And this is unique. This is the only shape for a potential of a proton. Point charge, a positive point charge. They're all going to look like this. So if you have a positive 2.5 coulombs of charge as a point charge, its potential is going to look like this. It's going to spike upward for large value or for small values of R, and it's going to dribble out to 0 for large values of R. The units will be different. It might not be nanometers. It might be kilometers on the R axis. And it might not be volts. It might be thousands or millions of volts on the vertical axis. You just got to work it out. But it will look like this. And so all positive charges are going to have a electrostatic potential that looks like this. And that's why voltages, electrostatic potential, is much easier to work with because when you're trying, a point charge is pretty easy to deal with, even electrical potential energy. It's not that hard. But when you're trying to assume and assemble the electromagnetic field of a system of charges, say that you're in a spacecraft on its way to the sun, and you have those big loops of hot plasma trapped in the magnetic fields, and those are going to generate electrical and magnetic fields, and that's the source. So you have this big source of electromagnetic radiation. You want to be able to figure out, that's a very complex array of charges, basically protons and electrons floating around in there, each going in different directions, or at least accelerating in different directions. So you got this loop out there, and you're in your spacecraft, and you're way out there. And say you're trying to figure out, well, how close can I get before the X-rays from that loop of plasma become too intense and start burning out my eyes or something like that, Or say that you know how high it is, then the secondary question would be, how much shielding do I have to put on my spacecraft to prevent my eyes from getting burned out by the X-rays? It's similar questions like that. So the idea is it's easier if you do potentials and electric fields of your source array and then worry about everything else afterwards. And then after you get all that finalized out or figured out in the end, then you figure out what your forces and your energies are. And it's usually easier to do that. Okay? So, nice little formula there. Any questions about this? Okay, let's keep going. The other thing that we did last time was parallel plates capacitor as our symbol for chapter 19. This is a really nice picture, and it shows something called equipotential surfaces. And we actually had a diagram last time. We had I think a proton, and then we had an electron, and then surrounding it we had two circles, dashed lines. And those were actually, everywhere on those circles was the electrostatic potential in voltage was equal. Because it was, K, Q over R, so everywhere R is equal, that's equal to a circle or a sphere. Now, in parallel plates, it's a little different. Your equipotential surfaces are not spheres because it's not a point charge. It's a flat array. And we talked about the uniform distribution of charge and the fact that the field lines were straight across. And they don't tip upwards, they don't tip downwards, except maybe at the edges of your plates. So when you get out there, the last millimeter or two of your parallel plates, you might get a little bit of non-uniform electric field. But towards the middle, where you got a whole lot of charge above and below every other charge, the field lines are going to be straight because the electric field is going to be distributed uniformly. So the distribution of your source charge determines the distribution of your field lines. The distribution of your field lines determines the strength and direction of your electric field. Okay, and so for this one, it's to the right. Now there's a formula down here at the very bottom. E equals delta V over delta S. That's a gradient formula. Kind of like a fancy word for, remember this from high school geometry class? Rise over run, the slope of a line. And in physics, rise over run can be a velocity on a position versus time graph. It could be an acceleration on a velocity versus time graph. And so the electric field on a potential graph is just the opposite of the rise over the run, the opposite of the slope. And we'll work on that in a few minutes. The other thing we talked about was the idea of capacitance, which basically encodes the structure of your plates, how far apart they are, how much surface area they have. And that basically controls how much charge every volt of your battery can load into the capacitor. So if you have a 1 volt battery, you can put a certain amount of charge into your capacitor. Okay, if you have a big capacitor, it'll all be in there. If they're, and if they're far apart or close together, that'll make it either easier or harder to put more charge in. If you have a bigger battery, like 6 volts, you can put 6 times as much charge in. Okay, because you have a bigger battery. Okay, and the capacitance encodes that. We found that the electrical potential energy and the potential itself, the voltage, is quadratic in the charge, in the voltage, and in the central field, E0. That's the symbol we use for that. So when I say quadratic, that means the potential energy is something times Q squared, something else times V squared, and something else again times E0 squared. We went over that yesterday on the document camera. So force as a gradient, and electric field is a gradient of V of R. And I'm going to ask you some clicker questions. Get your clicker handy. And let's see if you can get your brain on. Now, for this delta S, by the way, delta S is the symbol usually used for some generic coordinate, spatial coordinates. So X, Y, Z, R, any kind of a spatial, even if you have like tilted coordinates or curvilinear coordinates, S is sometimes used for a spatial coordinate in a generic term, meaning you can use it for any. Okay, so delta S means a change in the S direction, which is indicated by the black arrow at the bottom. And so in this diagram, delta S is SB minus SA, so it's positive. You're going in the direction of positive S, so SB is going to be a bigger number than SA. All right, so SB minus SA, big minus little is positive. All right, so it could be, 0.12 meters minus 0.113. And then your delta S is going to be the difference of those two. Okay? And it's going to be positive. Now, I want you to think about this. Delta V, VB minus VA is negatory. In other words, it's less than 0. All right? In this diagram. So go ahead and write down delta V, which is equal to VB minus VA. It's negative. So it might be, like minus 4.2 volts or something like that. All right? And that's in this direction. That's with the positive plates on the left over here and the negative plate on the right. All right? Now, I have a clicker question for you. Here it is. And go ahead and start reading and think. And hey, you guys, you won't find this problem verbatim on the test, but you might find a question that requires this much thinking about parallel plates. And notice that you have all the way up to option H. So what I want you to do, you know what? I did this the wrong way. I did it multiple choice, sorry. Let me change it to short answer. Okay, hit the refresh key on your calculator and type in a letter. You're going to have to use the up and down arrow keys to type in. I mean, if you want something other than A, B, C, D, and E. Okay? So look at your answers. And then use your up and down arrow keys and think. And then when you have A, B, C, D, E, F, G, or H selected, hit the send key. And it's definitely okay to talk it over with your neighbor, if your neighbor has a clue. Good. And hey, you guys, guess what? This is going to be on YouTube, so you don't have to take a picture of it. Although I know some of you will. One minute. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, let's see what you guys voted for. Somebody typed in 7C. This is strange. Oh my goodness. You know, only 2 people voted for this. But you know, that's true. It is high voltage over there by the positives. So if you voted for this, yeah, that's not bad. But you know what else is true? C. And seven of you voted for this. All right? And that's good. But I have to tell you that 130 of you voted for this. Because that's the best answer, okay? And B and C are the is the best answer. But I'm going to grade everybody correct for B, C, and F, all right? Matter of fact, I could do that right now. All right. Yeah, so the voltage near the positive side, you know, Whenever you have positive, some source array that's, basically positive, you're going to have high voltage there. You don't know how, might not know how high till you calculate everything, but it's going to be higher voltage. If you see some negatives, it's going to be lower over there. So you at least know that. And in the case of parallel plates, it's fairly easy to calculate. So delta V is negative, and that means that this quotient minus delta V over delta S will be positive, and for that reason, the vector E points to the right. Now that minus sign is actually quite important, and it's amazing, to me, to think about minus signs sometimes because, Newton's third law, the key is the minus sign in there. And in this one, the key is the minus sign. In the theory of relativity, there's a minus sign in the theory of four-dimensional space-time. There's a minus sign in the Pythagorean theorem when you apply it to four-dimensional space-time. So this is known as a gradient formula. It's kind of like a rise over run. You could think, and there's a minus sign out in front. And a similar one would be applicable for potential energy and force. So the force is minus the gradient of the potential energy, and that's for any potential energy. And then the electric field is minus the gradient of the electrostatic potential, no matter what the potential is. And this is why it is sometimes easier to work with point charge potentials and parallel plate potentials. And then at the end, when you've assembled your device or figured out your source, then you take the gradient like this, figure out rise over the run. You just look at the graph, you can figure it out, or you can calculate it with a computer, and then that tells you what the electric field vector is. So, I want to go to the document cam with you in a few minutes, so we'll take an early break today and then come back and do the document cam with you. And after the break, we'll also talk about the exam a little bit more. Okay, so break time. Okay, let's continue. We're going to talk about some chapter 20 concepts here. Let me get this thing. Okay. All right, that'll have to work. And I'm going to try to get some more ink for that smart pen, but for today we're going to have to use regular. So this is July 3rd. All right. Let's draw a parallel plate capacitor. And we'll charge it up with two charges, plus Q and minus Q, instead of putting in a bunch of little minus signs and plus signs. And what we're going to do is draw on the wires now. And here's the battery. Okay, and the wire connects both ends of the battery. So this is the positive end. This is the minus end. And this stuff, let's say that's copper wire. Oh, you know what? I want to make a mention of something from chapter 19. It just came back to my mind. There's some nice examples for those of you that are medically or healthily oriented, health science oriented, in chapter 19. The one that I thought was really easy to understand is the defibrillator, which is basically like taking apart a parallel plate capacitor and zapping somebody with the energy stored in the capacitor. You put the two plates, the two paddles on the chest of the patient, and somebody goes clear, and then everybody steps back, and then somebody hits the button, and hopefully gets their heart back to a regular sinus rhythm. That's parallel plates. So that's it. Stored energy. Energy stored in the parallel plates, and then you zap them out into another pair of parallel plates. So it's pretty nice. The other nice one was the electroencephalogram, the EEG example. That's kind of like at the end of chapter 19, which what they do there is they put two electrodes on your coconut, and then they measure the electrostatic potential between the two electrodes. So it's kind of like your head is a pair of parallel plates. But apparently, if you do that, you get regular brain waves, alpha waves and all that stuff. It's kind of cool. All right, so let's take a look at this. Now, it takes work to get electrons over to the negative plate. But guess what? A copper wire is not perfect. It's not a perfect conductor. It's good. Conducts. So what that means is that it takes a little bit of work to go every millimeter in the copper wire. Now, the individual electrons from the battery might not make it into the capacitor, but the electrons from this end of the wire in the copper will make it into the capacitor. And then if you disconnect it, they'll be stored in the capacitor because then the current won't flow any further. Now, this whole idea of a copper wire not being perfect means that it offers resistance. Okay, and we're going to study that in terms of a copper wire. All right, so I want you to draw, and this is going to be a physical conductor, a physical circuit, and we're going to model it and kind of get a quantity for the resistance, and then when we start working out circuit problems, which I understand you guys are doing in lab, parallel and series and all that stuff, I'll try to give you some mental counseling about that today. Hopefully it'll help. I know labs are, I don't know if I should apologize, but I do feel for you guys because the labs are notoriously out of sync with lecture. It's just, I have all kinds of comments I could make, but I'm not going to make any comments about it other than that. But anyway, so hopefully this will help you with that. And because what you guys are doing up there in the lab, well, I shouldn't say that. Maybe you guys are measuring resistance, but generally what you do with circuit problems is you learn all this physical stuff, and then you approximate it as every wire in a schematic diagram is a perfect conductor. So we're rapidly going to forget about everything I teach you for the next 5 minutes. But anyway, so let's make a length of copper wire, another cylinder. Physicists are not that smart, so we only know a few basic shapes: circles, cylinders, stuff like that. Okay, so this is copper, Cu. And the valence electrons, or the conduction, I should call them conduction electrons, they're easy to move, but they don't move for free. So every millimeter of travel requires a little bit of work that's dissipated. So getting electrons into the parallel plates means you first have to get them through the copper, so that's going to require a little bit of work. And then you got to get them into the plate. So, and as I mentioned last time, it's easy to get them in early. It's harder to get them in late, even if you have a perfect conductor. All right? Now the resistance, capital R, is a function, whoa, there we go. It's a function of the more resistance you get with length. So let's make a note of the length here. So let's say that this is the length of copper wire from your battery up to your plate, okay? And it's going to require a little bit of, a few centimeters or whatnot. So the formula is going to have L in the numerator, but then it's going to have the cross-sectional area in the denominator. The more area you have, the less the more open the electrons are fighting to get through, okay? They're trying to elbow their way through, okay? And if you make the wire broader, more cross-sectional area, then they don't have to fight as much to get through, okay? So these are the geometric factors that of the wire itself, no matter what the wire is made of, the length and the cross-sectional area. Now the property of the wire itself, the property of the copper, is a proportionality constant, and it's customary written rho. Okay, now that's not the density, that's called the resistivity. Okay? And what this encodes is the resistivity, and you can read about it in chapter 19. This encodes the properties of the conductor, in this case copper. Okay? So, basically how easy is any, ounce of copper, any gram of copper, how easy is it to get an electron through? Okay? And then these two factors, the size of the wire. So a physical wire is going to have a length. It's going to have a cross-sectional area. And it's going to have a specific substance that it's made out of. You guys are passing notes up there? This is like 5th grade or something. I haven't seen that in a long time. I don't know. Anyways, so the resistance, now, you lose energy from the electrons to the copper. So the copper is going to absorb some. It's going to get hot, basically. Sure. Okay, so the electrons are going to lose a little bit of energy, and so you got to keep pumping them through there. You got to have a good electric field, but they'll basically go. Okay, if it's copper. But they're going to, so every millimeter that they go, they're going to lose a little bit of, they're heading to the parallel plate, the negative plate, and they're going to lose some energy. Okay? So they're not going to go out. It's not like going through space. All right? This is a real metal conductor. That also means they lose voltage. As they go through the copper. Okay? Now, if you have a lot of charges going, if you have a lot of current, and each of those electrons in the current is going to lose a certain amount. Okay, so it's, let me go to the next page here. I'll photocopy these for everybody, just like I did yesterday's. So delta V in the wire on the way through, it's proportional to R, to the resistance, okay? And the resistance encodes the size and shape of the wire and also the nature of the substance. Is it made of copper or is it made of gold? Gold's an even better conductor, even lower resistance. It is also proportional to how many charges per second. So if you're sending a lot of them through, then each electron is dropping a certain number of volts. And so if you got a lot of electrons going through, that's a lot, just multiply by how many electrons you got. So the more charge going through per second, the more voltage gets dropped. All right? So how many charges per second? So that's delta Q over delta T. The amount, so the amount of charge past a point in the circuit, you could think of it that way. And because it's a circuit, you're not going to lose any charges. So they're not going to disappear, out the side of unless you get a short circuit. Then it'll, cause an arc and you'll lose some. But if it's insulated, and stuff, it's not going to short circuit, then you don't lose any of these you don't lose any electrons. They just rearrange themselves. Now this quantity here is also known as the current. And the symbol for that is capital I. And some textbooks use lowercase I. But our textbook uses I. That's the current. And it's measured in amperes. An ampere in the metric system, believe it or not, the ampere is actually the fundamental unit, not the coulomb. It's 1 coulomb per second through a circuit at a given point. Okay, so if you put a little current meter there, counting electrons as they go merrily along their way, or counting every 10th electron, or what have you, then you're measuring the current in amps. So this relationship of current resistance can be written in this way. Delta V equals IR. And that's across any resistor. Now, if you look around the room, anything that's producing light is a resistor. It's doing, especially the incandescent lights. The incandescent lights in the room are producing light because they are hot. And so they're losing heat, basically. And the way an incandescent light works, you don't make the filament out of copper. You make it out of something that's hard, that's not a good conductor. It will conduct, but it's not a really good conductor. So because it's not a good conductor, the electrons trying to get through burn off a lot of kinetic energy. And just like the space shuttle coming in from orbit, it's got a huge amount of kinetic energy to burn off before it gets down here to Kennedy. It's got to land at 200 miles an hour, and it's up there 200 miles up in space, 18,000 miles per hour, plus a lot of MGH to get back down to the ground. It's even more kinetic energy. And it's got to burn all that off by the time it gets down here to Kennedy. Okay, and the same thing here. In a filament, the electrons are trying to go through there, but they got to burn off a lot of kinetic energy, and that heats up the circuit. Okay, now it's not going to heat up copper very well. I mean, it'll heat it up, but not a lot. Gold the same, because gold is a good conductor. So it's not going to heat up a whole lot. But something like tungsten, yeah. Matter of fact, I should look up the very first filament that... Who invented the light bulb? Thomas Edison, right?
Well, like even at the most popular model, supposedly there were other guys before him that also came up with like predecessor to the light bulb, but he's like the first one to actually make a patent for it.
Well, anybody that's ever caused something to glow red hot, that's the same principle. So anyways, the light bulb works on that. So any resistor in your circuit is going to drop volts. And this is the formula for it. Depends on how much current you got through there. So if you don't have any current, you don't have any resistance, you don't have any voltage, dropped. Okay, but if you do have some current, you're going to drop some volts. And if it's a high resistance or low resistance, you're going to drop more or less volts. This is known as Ohm's law. The guy that figured this out, George Ohm. Every electrical engineer in the universe has Ohm's law imprinted in their mind. Here's another version of it. V equals IR. Okay. So, let's do some circuits. Let's put a battery. Here's the symbol for a battery. I think you guys know that from lab. This is the plus side. Now, we're going to forget everything we just learned. And we're doing a schematic diagram here. So we're going to think of all the resistance being in a single device. And you use a squiggly like that to represent it. Okay? Right. So there's energy that's lost as light or heat, and that means that you've also lost, because remember, potential energy and electrostatic potential are related. So if you know that energy is being lost, you can also say that voltage is being dropped. Okay? So any device that does any kind of work, whether it be a light bulb or a machine, it's going to drop some volts from the input to the output end of the machine.
So that's the difference in voltage between the battery and the parallel plate?
No, it's the difference from point A to point B in your device. And this is what I was just trying to say, that in this kind of a schematic diagram, we're assuming that out here in this wire, this schematic diagram of a wire, there's no resistance, and that it's all here. And that there's no resistance inside the battery, that this is only electromotive force. Script E is what they usually use for that. That's the source of voltage. Okay, so that's what we're assuming here. A real one, you'll have a little bit of voltage dropped all the way around here. By the way, another thing that we have to get used to with circuits, it's a pain in the boop, and that is the idea of conventional current versus physical current. The physical current is electrons moving. The conventional current is the hypothetical direction that positive charges would go. So they would go away from the positive terminal, go through the resistor, and all the way back here. Okay, so at this resistor, delta V is equal to VB minus VA. All right? And let's see. So this is going to be in volts. So the resistance is equal to delta V over I. So that's volts per ampere. Okay, so the unit of a resistance is volts per ampere. And every device has a resistance, every physical device, no matter how small. In other words, it means it's like saying, how many volts do I lose in this device for every ampere of current that I put through the device? All right, so that's what it's telling you. All right, so it encodes the amount of electrical work, but it's not, I shouldn't say electrical work, electrical potential. All right? The fancy term for volts per amp is the ohm. And I think you guys know that. The symbol is omega. All right? So let's do a simple calculation. Let's say that my battery, the EMF in my battery is 6.0 volts. All right? And let's say that I have an ammeter here. Yeah, let me cross that out. That's confusing. Let's say that we measure the current. And the current is 0.2 amps. And I'll put a dot here. We'll measure it at, let's not call it C, let's call it H. Point H, we measure the current, it's 0.2 amps. Okay, now this is a perfect schematic diagram, so everywhere in this wire, there's no place for the current to go, so it's really 0.2 amps everywhere in the wire. 0.2 amps up here, 0.2 amps here, 0.2 amps fighting its way through this resistor, a light bulb or whatever it is, a machine. 0.2 amps here, here, all the way through. Now, if you get branched circuits, the current can split. But for this one, it's only one way in. One way around, that's it. So let's figure out the resistance. The resistance is equal to delta V, so that's 6.0 volts, divided by 0.2 amps. And that's 60 times 5, so that's what? 300? Anybody verify me on that? 60 divided by 0.2?
Is it 60 or 6?
Oh, yeah, it is 6.0. Okay, so 6.0 times 0.2, that's 30. 30, okay. Good. 30 ohms. Yes?
Sorry, what does the letter E stand for?
The letter
Is that just like
E stands for electromotive force, EMF. That's like, I think it's Michael Faraday's term for voltage. You know, a lot of the terms, it's not really a force, but people still use the term. It's like a lot of stuff, you know, that.
so is E just like the electromotive force kind of like delta E?
Yeah, it's the amount of voltage. You know, it's the voltage label on your battery. You know, it'll always say, 1 volt or, 6 volts or, like 12 volts or whatever it is. Okay. Another question. All right. Let's do another circuit. Battery. Resistor number 1. resistor number 2. All right. And let's say that the EMF is 6.0 volts again. And let's say that R1 is 20 ohms. And let's say that R2 is equal to 4 ohms. Okay? Now, this is, what kind of circuit is this? No, it's not parallel, it's series. It's confusing sometimes. This is a series circuit. Now here's how you think about it. A series circuit is a circuit in which the current, here's a conventional current, it zips out of the battery, and it heads for resistor 1. Then all the current goes to resistor 1. There's no other place for it to go. And then it comes out of resistor 1. And then it zips around the back stretch here, and then eventually it heads into resistor number 2. Now it's got to get back to the battery. All right? It's going to get back to the battery because we have an electric field all the way to the battery. And there's an electric field set up inside the conductor. That's what makes the electrons move. So it's going through, so it's battling through R2. And it gets back here. And by that time, it's dropped all 6 volts. So let's make a note. All 6.0 volts are dropped on this loop. So from the battery to R1, in R1, from R1 to R2, in R2, and then from R2 back to the battery. Now, we know that physically this is happening. Now, the schematic diagram is an idealization. We're thinking of it as if the wire doesn't really hold any resistance. But physically, we know that there's going to be some resistance every centimeter of wire, so you're going to drop a little bit between the battery and your device, number one. Then you're going to drop some in the device, and then you're going to drop some between the two devices because you got another few centimeters out here. And then getting through the second device, you're going to drop a few more. And what we're going to figure out is how many we drop. Okay? And then the last one, down to 0. You drop all the way down to 0. And you're back at the battery. And then your electrons can get juiced up again and goes and start doing another lap. Right? Now, what that means is that 6.0 volts is equal to current times R1 plus the current times R2. And we're ignoring the stretches of the wire. Okay? Plus the stretches of the wire. We're going to imagine that those are zeros. So we're just talking about resistance 1 and resistance 2. Now this is a way that you can figure out the total current. All right? So now let's put in the resistors. 6.0 volts equals current I times, resistance 1, 20 ohms, plus resistance, current I times resistance 2, 4 ohms. Wait wait a minute, so that's actually equal to I times 24 ohms, all right? That's what we could figure out now. We can get I by itself. So this is what we call easy as walking through the park. All right, so I, and this is 6.0 volts over here. So I is equal to 6.0 volts divided by 24 ohms. Okay, two significant. Oh, bring it up, yeah. That's all right. 24 volts. Okay, so that's 0.25. Okay, so, and it's amps. Capital A is the symbol for amperes. Okay, so there's your current. Now, you can go back and see now how much you missed at, how much you dropped at resistor 1. Delta V1 equals I times R1. Okay, so 0.25 amps times 20 ohms. Okay. So that's, what's 0.25 times 20? That's 5.0. Okay. So now you can figure out R2 as well. Because R2 is going to be the rest. So figure out R1 and then R2 is the leftovers. Okay? Question? Yes?
So having all of the volts drop by the end, that's a constant? Like between the two resistors, having the 5 and 1 equals 6, that's always going to happen?
Yeah, in general, it's always going to be this E equals IR1 plus IR2 plus, as many resistors as you have. Okay. So they're all going to drop. Every resistor is going to get a little bit of voltage drop. Now, if you have a ton of resistors in there, they're not all going to drop 6 volts, or they're not all going to drop 5 volts. If you put another resistor in there, a matter of fact, I want you to think about this. Let's do some thinking. Okay, you put another resistor in there. All right, so R3. So you put R3 in there, and let's say that R3 is, what was R2? Let's say you put another 4-volt job in there. Okay, is R1 going to drop 5 volts? No, it's not. The equation tells you that, but why does the equation work that way? What happens to the current through R1 if you put another resistor in there? It's going to decrease. The more resistance you put on your circuit, the less total current goes through the circuit. Now, if you have parallel branches, that's not the case. But with a series like this, in other words, one stream of electricity all the way through, the more resistance you put, but still, in the end, they'll all, however many you got, they'll all add up to the battery or whatever your voltage source, happens to be a generator or something like that. Question? Elizabeth? No, I didn't. I just subtracted 5 from 6. But yeah, you could do it that way too. The question was, did I multiply 0.25 amps times 4 ohms? And the answer is no, I didn't, but I could have. I guess I just went 6 minus 1, or 6 minus 5. So, question. Alexis.
So it doesn't matter where you add the resistor?
It doesn't matter where you put it. The question is, does it really matter where you put the resistor? In a schematic diagram, no. I mean, and that's where you have to, use some common sense eventually, because you're building a physical device, like say you're building a defibrillator, a new defibrillator. You go to med school. My little sister is a cardiologist. She's an electrocardiologist. So she knows all this stuff. And let's say that you become an electrocardiologist. You know how long she had to go to school for that? A long time. But she's making some big dineros now. Anyway, say you become an electrocardiologist and you're devising a new defibrillator. And you're okay. I want to adjust the current. So you got to figure out where to put stuff. You don't want to have something, like by the handles where there's a lot of wrist action. Because you might wear the cables out and then it'll short circuit and then you'll zap yourself, and instead of the patient. So you don't want that. So physically, yes. Eventually, when you put it together, but you're going to get an electrical engineer to do that. But yeah, I mean, theoretically. But remember, these schematic diagrams are idealized. Zero resistance on the wire. Matter of fact, a lot of schematic diagrams, zero resistance in the battery. Although, I think probably in your lab manual, you may see a little tiny lowercase r and a little teeny squiggle right next to the battery to represent the internal resistance of the battery. Because the battery is basically some parallel plates and some paper soaked with acid, so that you have ions flowing back and forth. And that's it. Some variation of that, carbon and zinc or lithium, different metals and stuff, but basically that. So there's going to be some internal resistance, but for basic circuits, you ignore that. But in a real circuit, you would put a little tiny r, lowercase r, and a little squiggle right next to the battery to symbolize the internal resistance of the battery. So, that is one of Kirchhoff's laws right there, by the way, you guys. Right there. Let's take a look at parallel circuits. Hopefully this will give you guys some... Was that helpful to look at that and talk your way through that? All right, let's do another circuit and then we'll dismiss. Let's do parallel. All right. So we'll do the simplest circuit of them all. A battery and two resistors. Yes?
If you worded this in the word problem, how do we know which one is parallel and which one is?
The picture, so the question is, in a problem, how do you know if the circuit is parallel or not? Well, first thing you do is look at the circuit diagram, if you have it, all right? And I'm going to draw one here, and I'll describe how to decide whether it's parallel or not. If you don't have a diagram, you got to read the text and figure it out. I would never do that. I'll always give you a diagram. So on Thursday, I can't tell you what's going to be on the test, but if by chance you have a parallel circuit of some kind on Thursday, I'll give you a diagram. So I don't want you to, I want you to think. I don't want you to memorize. I don't want you to regurgitate. I mean, you can get any number of engineering students to do stuff like that, I mean, you're going to be doctors, right? I mean, that's what many of you hope to do. You got to, doctors and nurses, I mean, you got to be able to think. I mean, You know, we were talking about it in office hours. You know, you're a surgeon. You know, you're either a medical doctor or a surgeon. You're a surgeon and you've got somebody's intestines open to take out their appendix. And you look at it and you say, oh my God, that's a cancer tumor on his colon. Now what do I do? You can't memorize something like that. You just got to be able to think. And you got to think fast. But for circuits, I'll give you a diagram. Don't worry about that. Now let me draw a parallel circuit and I'll describe it. Okay, first, battery. Battery, always a battery. Okay, I'm going to put my first resistor on the back stretch here. All right, it starts with a regular circuit. You know, here's my E. Here's R1. And we know how to handle that. There's no great shakes about that. You know, all the potentials dropped at R1. I mean, that's a simple circuit. But that's not what we're building a parallel circuit. All right, now parallel to this branch is another branch. So go upstream of R1 and downstream and just inch out here to the side. Just kind of easy does it. And let's call that R2. Okay, now let's put in a plus. I always put a plus sign in here. And we'll put a couple arrows. And we know that the current goes through R1. But hey, you guys, look. If I cover up R1, R2's on a regular old circuit. So I'm going to drop 6 volts there. And that is the key. I drop 6 volts at R2. And I also, if I don't have that one, I have R1, I drop 6 volts there. And there's one more thing. Right here is a branch point. The circuit comes to a branch. And then right down here, it comes back in. All right? So let's take a look at these branches. All right? Whatever branch is off over here, this is I2. All right? It's going through resistor number 2. And then whatever goes through R1 is, we're going to label that I1. Now those two currents might be different. Depends on what R1 and R2 are. So let's put in R2 equals 10 ohms and R1 equals 6 ohms, just for nice round numbers. Okay, so you're going to have different currents. And let's say that the EMF is good old 6 volts. All right. Now, I want you to listen carefully. The tale of two cities. I'll put a letter A here. No, I'm not going to use A. H. And then down here, letter M. No, you can't use J because J is another symbol for current. So, okay, so those 2 points. So the tale of two cities. The total current that leaves the battery is I. It gets to point H and a little bit slides down here through R1 and a little bit slides through here through R2. But at point I, or at point H, the 2 currents, I1 and I2, add up to I2, or to capital I. Okay, they add up. And that's because of conservation of charge. Okay, so the electrons don't go away. The putative positive charges in the conventional current don't go away. They do split. They rearrange themselves. Okay, so you get some amps. So I2 is going to be a different amount of amps than I1. But they're both going to add up to I, the total current. All right, so then down here at M, I1 plus I2 join, and they form a total return current I. So you haven't lost any. You've split it up at point H, and you've rejoined them at point M. So no tricky stuff. You know, it's all there. It's just be rearranged and then recombined. It's all there. All right? Now, the R1 loop. The loop of R1. Drop 6 volts. Ding. You know, whatever E is, it's the only thing on that loop. So forget about all this stuff up here. And just think about that one loop. Ding. It's the only resistance in there. So all 6 are going to drop there. All right? So V1 is going to be 6 volts. All right? Now, cover up R1. I'll cover it up with my thumb. Now over here, that's the only resistance on this outer loop, the outer branch. So we're going to drop all the outer loop. We're going to drop 6 volts there too. Now, we're not going to drop a lot of, it's not going to be carrying a whole lot of current because remember, the current splits. You know, if I have 10 amps coming out of the battery, I'm not going to have 10 amps going through either R1 or R2 because it's going to split. All right? But I am going to drop 6 volts. All right? Because, and here's the essential definition of a parallel circuit. Okay? If the current can take one or more independent paths through a loop and get back to the voltage source, it's a parallel set of circuits. Okay? And this one can do that. You can go through loop number 1, but you know, you're up there, you're an electron, you're approaching station H. Next stop, station H, transfer to loop 1 or loop 2. And the electron's he can't go on both at the same time. So he's going to go on 1 or 2. And those are and then but then approaches station M, transfer back to the express train, back to the battery. So then, so you know, when you're getting on an express train, you know, you got to elbow your way back in there because everybody's funneled into the express train. All right. So now look at. So what we're doing, you guys, you know what we're doing? We're thinking, and I'm narrating my thinking. What we're doing is pulling stuff apart, and we're about to put it back together. Question?
Okay, so since you said the parallel circuit is when you have more than one independent path versus like the current can split, does that mean
Right.
series circuit is when there's only one path and there's no way to
Series circuit? Yes, series circuit means you've got only one path, and you may have more than one resistor, but the current is going to go through all of them.
Okay, so in a series circuit, the current will be the same throughout the entire circuit?
Yeah. The voltage dropped will be different at each resistor, but not the current. This one, the currents are changing.
And the voltage is the same?
Right. Because each loop is independent. So, so an electron approaching station H, better get off, go through loop 1. That guy's going to drop, he's going to have to drop 6. And that's the only place to drop it. And then the guy that goes over here to loop 2, I'm going to go to loop 2. And he's going to drop it here. That's the only place to drop it. All right, so that's this stuff here. All right, now, let's put it all together. And hopefully, you guys will have a little bit of happy thoughts when you go to lab. Let's take this equation right here. We could easily use the one right below it, but the total current is equal to I1 plus I2. Very nice. Oh, Ohm's law. V equals IR. That means that I is equal to V over R. Nice. And they're all dropping 6. So this is the same as saying 6 volts divided by R1 plus 6 volts, 6.0, divided by R2 equals total current. My wonderful students, can you figure out the total current now? Yes. So wonderful. Okay, so you can figure out the total current because we have the numbers for everything. Let's do it. 6.0 divided by, what was R1? 6 ohms. Okay, so this is 1 amp. Oh, that's the current. 1 amp for current number 1. This one. 6 volts divided by 10. Ooh, that's 0.60, so 0.60 amps. Okay, so you can see a little bit less current goes into loop number 2. And why is that? It's got more resistance. I wish I had a clicker question for this. Do you realize how much I could torture your minds with questions about just this circuit? I mean, I could torture Daniel Reinhardt's mind, or any grad student, you could. And I've seen professors, like physics grad students at their PhD exam, when they're doing their thesis defense, they have this big fancy paper that they write, 120 pages long about copper superconductors or something, whatever they're writing about. And then once you defend that and your PhD defense committee says, okay, then at some schools, like where I went to grad school, they open up the questions, Dominic, for any question that the committee wants to ask. So there was this one guy ahead of me in grad school. God love him, Nick Pinto. Long may he reign. And he wrote a wonderful thesis. He got a good job when he graduated. But when he finished his thesis and they opened it up to general questions, there was an instructor, a professor, Dr. Francis. He took a can of Pepsi and he put it on top of the overhead projector, and he said, Nick, draw the forces that are acting on this can. Now, this professor was a specialist in physics education, so he kept asking Nick Pinto questions. Now, what about this, and what about this? And by the time, 15 minutes later, Nick Pinto did not know which way was up, but he still got his PhD. So we're not done, almost done. So my point is, a question like this, you could really, even grad students, you could torture their minds with this. But I'm not going to, I still want to talk about the exam. All right. Anyways, we've got everything in this circuit figured out except for the total, but that's easy now. Now, so that's good. Total current is 1.6. And you guys, by the way, the equivalent resistance is found from this equation. So you take your EMF of 6 and you divide by R to get 1.6 amps. So the equivalent, and I'll write it REQ, that's equal to V divided by your total amps. So this is the resistance that would be the equivalent of these two in parallel. All right, so it's 6.0 volts divided by 1.6 amps. So what is that? 3 point what? 3.7. So REQ is 3.75. And so now, let me go back to this equation here again, and I'll now rewrite it in terms of voltages. Okay? This is the ratio for total current. So V over REQ equals, okay, loop 1, V over R1 plus, here we go, plus V over R2. And hey, you guys, as many as you have. And the volt, if they're parallel circuits, the voltage drop is the same. All right? So this is 6 volts numerator, 6 volts numerator, 6 volts numerator, 6 volts. But then the resistance is, and I know in lab you guys are probably going to want to figure out the equivalent resistance. This is the equation that you use. Matter of fact, you can cancel out the V's and just write it this way. 1 over REQ equals 1 over R1. So that's why it comes from the conservation of current, conservation of charge. And hey, you guys, there's a lot of equations in physics that are like that. You know, that's related to the center of mass calculation. Okay, about the exam. Let me go back to just a moment. Don't dismiss yourself yet. Couple things I want you to bear in mind. First of all, when we come back on Thursday, we'll have about 45 minutes. We'll do a wrap. We'll do a little bit of Bernoulli, a little bit of electric field, a little bit of voltage, parallel plates, a little bit of circuits, just to get your mind warmed up. So I'll give you some homework to study. Now remember, your lecture notes are, and I'll get these uploaded into the web courses directly. Your lecture notes are the priority. Make sure that if you want to read extra in the book, it's related to, read whatever you want, but be sure to read what's related to the things that I talk about in lecture. All right, so we're not going to go deep into Gauss's law from chapter 18, and we're not going to go deep into Archimedes' law from chapter 9 or chapter 11. But you think you're going to see any parallel plates on Thursday? Yeah. You're going to see any kind of a polygon with charges on it? Yeah. You think you're going to see any kind of a circuit? Yeah. All right. Now, one last thing. We got written homework. I haven't decided what to... You know what I think I'll do? Monday? I didn't say that. No, don't say that. Don't put that in my mind. Yeah. I'll put the homework up in web courses by 9 p.m. tonight. That'll be your written assignment to hand in Thursday. And I think I'll also put a web courses assignment covering chapter 19 calculations. Kind of like, I know some of you have done the extra electric field practice in web courses. I'll do one like that for potential, point charges and parallel plates and stuff. And then the written assignment, I'll put the PDF of it in web courses, and you do the same thing. And then on Thursday, I'll select about 40 of you. Do you want to know who it's going to be? It's going to be somebody with last names between A and L, or maybe somebody from Q through Z. But other than that, I can't tell. But I'll tell you on Thursday morning. All right, you're dismissed.